I'm going to be talking about a novel in situ soot oxidative reactivity measurement method, and using that to look at the effects of lube oil ash on GDI soot oxidative reactivity in a catalytic GPF. So the motivation of this work is the importance of soot oxidative reactivity and its measurement methods. The soot oxidation rate is fundamental to understanding the kinetics of GPF loading and regeneration. This is especially true for GPFs as opposed to DPFs because SI engine exhaust is much hotter than diesel exhaust, so passive GPF regeneration occurs frequently during driving cycles, and it's desirable to have a decent amount of soot loaded on the filter so that you can enable high filtration efficiencies. And understanding the loading and regeneration rates is important to that. Oxidative reactivity is usually measured with thermogravimetric analysis, or TGA, and basically you load a soot sample into a crucible that's suspended on a microbalance and then in a furnace. And the schematic on the right shows a TGA, and basically you determine the oxidation rate based off the change of mass of the soot over time in the furnace as it's oxidized. And because TGA is an offline method, it may not accurately predict actual oxidation rates of soot in a GPF. And this is because the nature of the soot may have changed slightly when you take a soot sample and kind of compact and load it into a crucible, as opposed to what the kind of macro morphology of a soot cake is, the soot particles filling pores and then layering on top of each other. Additionally, with TGA, you're relying on oxygen to diffuse into the soot, whereas in a filter, you have the exhaust flow flowing through the soot cake at all times. And lastly, the influence of a catalytic GPF wash coating on oxidation rates can't really be explored through TGA, and we think there may be effect of catalyzed wash coat loading on the oxidation rate of soot. So we know that certain lube oil additives enhance or inhibit soot oxidation rate, and they do this when ash particles are embedded or decorate the soot particles. And then these ash particles act as catalytic sites or inhibitor sites and affect the oxidation rate. And the image on the right kind of shows a picture of that. In the top picture, you have kind of free-floating suspended particles, and then once those particles combine and are loaded onto the filter, they kind of compact, and you can see the green dots are what you can imagine are ash particles interacting with the primary particles of the soot agglomerates. So in this work, we developed a novel method for looking at oxidative reactivity of soot using various lube oil formulations to induce different soot reactivity to demonstrate the method. So this shows the experimental engine and sampling system. The engine was a 2-liter naturally aspirated BMW GDI engine. It had centrally mounted spray-guided piezo injectors. The engine was controlled with LabVIEW hardware and software, so we had full control over injection timing and equivalence ratio and everything like that. The sampling system included an AVL emissions bench, so FTIR, FID, O2 analyzer, and secondary CO2 analyzer for measuring gas phase species. And then the particle instruments included a microsoot sensor at the engine out sample location, and then tandem EEPs upstream and downstream of a three-way catalyst wash-coated GPF, measuring just solid particles. So the CS1 and CS2 are catalytic strippers, and the catalytic strippers remove any volatile or semi-volatile materials, so that the particle size distributions measured by the EAPS are just solid particles. And the tandem EAPS upstream and downstream of the GPF allow us to measure real-time size-resolved filtration efficiency. The test conditions and oil formulations, we tested 3 oils. The first one is ZDDP oil. So it's 100% PAO base stock with 10,000 ppm of ZDDP. A non-detergent oil that was just 100% PAO base stock with no additives. And then a calcium oil, same PAO base stock with 5,000 ppm calcium sulfonate. And then 4 GPF loading engine conditions were tested, using 3 runs at each condition for each oil. There's a non-oxidizing condition, lower temperature, then a mid-temp with moderate soot, a high temp with moderate soot, and then a high temp, high soot condition. So for the low temp non-oxidizing reference condition, this is used to set a baseline for the GPF loading. Equation 1 shows a mass balance for the GPF. And for the non-oxidizing condition, there's no oxidation. And so it's just mass of soot on filter is equal to mass of soot in minus mass of soot out, which we're measuring. And so we can get this curve that you see on the right, which is filtration efficiency as a function of mass of soot on the filter. And then with equations 3 through 6, we can correct oxidizing conditions for temperature and flow rate, so that we can determine the mass of soot on the filter for an oxidizing condition. Once we have mass of soot for an oxidizing condition, we can use equation 2 to calculate the oxidation rate. So for this is the high temp moderate soot. I'm just showing one of the test conditions for results, just for time. But so this is the high temp, lower soot concentration, GPF temp around 560 C, around 2 milligrams per cubic meter of soot. And then the top 3 curves, those are the filtration efficiencies of the GPF as it's loading, and this is filtration efficiency just at 100 nanometers. And the green curves are the calcium, and you can see that the filtration efficiency of the calcium doesn't really change over time. So this shows that the GPF isn't loading, and basically all the soot that's coming in is being oxidized. And so this is the reason that the oxidation rate, which is shown in the dashed green line, is much higher than the other 2 oils. So it's about 5 times higher than the non-detergent oil. So this kind of shows that the catalytic surface of the GPF is playing a part. So it's the difference between oxidation of a soot cake layer as opposed to oxidation of free particles on the catalytic surface. Additionally, we can see that the ZDDP, that oxidation rate is about 30% lower than the soot when using the non-detergent oil. And this has been shown in other literature that ZDDP inhibits soot oxidation and that calcium enhances oxidation. Also, if you look at the the loading curve, or sorry, the oxidation curves for ZDDP and the non-detergents. So those are the orange dashed lines and the blue dashed lines. You can see that they start high and then plateau at kind of an equilibrium value. And this is, we think, because initially during the loading process, there's very little soot cake. And so the ratio, basically the surface to volume ratio of the soot cake is much higher. So therefore, there's more soot in contact with the catalytic surface of the GPF, which would increases the oxidation rate. And then it eventually levels out once the thickness of the soot cake layer equilibrates. So in summary, we demonstrated a new measurement method and showed that ZDDP inhibits soot oxidation while calcium enhances the soot oxidation rate. And there's a difference between the inherent soot cake oxidation rate and the oxidation rate at the interface of the soot cake and the catalytic surface. Basically, free particles on the catalyst surface oxidize much faster than those in a soot cake. And because of that last point, the specific soot oxidation rate in a catalytic GPF is dependent on soot load, where that might not be the case in a non-coated GPF, where the oxidation rate would just be that of its inherent soot cake. So, thank you.